First I'm going to prove that the set of all real numbers is not enumerable. It's what's called uncountable. Our proof is by contradiction. Let's suppose that we have an enumeration of the real numbers, which means that the set of real numbers can be listed as x1, x2, x3, and so forth. Now for each one of the i's from 1 to infinity, we let di be any digit which is not equal to the ith digit of the expansion of xi. We can take the decimal expansion if we want. And then we define the real number x to be the real number whose expansion is 0.d1, d2, d3, and so forth. Now since x is a real number, it has to be equal to xi for some I. But that's the ith digit of x is d sub I, which is not equal to the ith digit of xi by definition. And that's a contradiction. Cut. Are you done, Yusuf?
Okay.
All right. The set of all Turing machines is enumerable. Well, the proof is quite simple because every Turing machine has a string which is its description. And the set of all these strings is a language, and every language is enumerable. There is a machine which enumerates or writes the decimal expansion of the real number pi, the familiar number that the circumference of a circle to the diameter. And such an algorithm, we could write a computer program which would just print those numbers. Another way to put it is that we could have a machine where you put in I and it gives you the ith digit of pi as an output, so it's a single output. That machine would be, if this one is possible, that one is possible, and vice versa. Now the question is, what about an arbitrary real number? Let's say that x is a real number. Does the machine which prints out or computes the ith digit of x exist? Does that machine exist here? Let's call that m sub x. And of course it exists if x is pi. It also exists if x is the square root of 2 or any rational number or the cosine of 27 degrees, or in fact almost any number that you would normally think of. However, it does not exist for every real number. Here's the proof. There are uncountably many real numbers, but there are only countably many machines. Therefore, there are not enough machines. You can't have more than one of these. You can't have more than one number x for any given machine, so there aren't enough machines to do this. It's not even possible to always build a machine which can approximate a real number. Take an arbitrary real number. An approximation machine would be one where if you put in any fraction, it will tell you whether the value of that fraction is less than x. It is less than x or it's not less than x. Now that sounds like a very simple thing to do. If I give you the square root of 2, you can certainly tell me whether 3/4 is less than that or more than that. However, it is not possible to have a machine like this for every real number x. And the proof is very simple. There are only countably many Turing machines, and there are uncountably many real numbers, so there aren't enough machines to do this for every real number. Okay, for any Turing machine M, we can define L of M, the language accepted by M, to be all the strings which cause M to halt if given as an input. Now we'll say that that means if it halts with input W, we'll say that M accepts W. Now we talk about, these are just different ways of phrasing it. we define halt to be the language consisting of all strings of this form. The description of a Turing machine and then a string W, which is accepted by that Turing machine. In other words, that this machine M halts with input W. Now what we're going to prove here is that the language of halt is undecidable. All right, how are we going to do that? It will be a proof basically by contradiction, but the first thing we do is define the diagonal language. And this, remember how we used diagonalization to prove that the set of real numbers was not countable? Although it's a little bit concealed, language is actually defined in terms of a diagonalization. So the diagonal language is the set of all Turing machines descriptions such that that description is not a member of the language accepted by the machine M itself. Now we're going to prove that the diagonal language is undecidable, and that proof will be by contradiction. So suppose that L sub diagonal is decided by some Turing machine, which we'll call M sub diagonal. Now what that means is that if we input the description of a Turing machine into the machine M diagonal, it will output a 1 or a 0. A 1 if the description is a member of the diagonal language, and a 0 if it is not. We'll see how that will result in a contradiction. Now, by definition, see, M is a member of the language accepted by M if and only if M is not a member of the diagonal language. This statement is true by the definition of the diagonal language. On the other hand, M is in language accepted by M sub diagonal if and only if M is a member of the diagonal language. This fact is true by definition of M sub diagonal, namely a machine that accepts L diagonal. All right, now for both of these two statements, we can use universal instantiation, replacing the variable M, which is universal, by the instance where M is equal to M diagonal. And so now we get the following two statements. From this one we get that, and from this one we get that. This description of N diagonal is a member of the language accepted by L diagonal if and only if M is not a member of L diagonal. We do that by instantiating the first one. By instantiating the second one, replacing each M by N diagonal, we say that I have to write M diagonal here. Oh, sorry, I missed that. And this, of course, up here, these are descriptions. All right, now, replacing M by M diagonal in each of these two statements, we get that if this description is accepted by the machine, then its own description is not a member of the diagonal language. On the other hand, if it's accepted by its own machine, it is a member of the diagonal language. Now these two facts contradict each other, don't they? Except that's actually a fallacy to say they contradict each other, because they don't. Because the only way they would contradict is that if this machine actually exists. And so we now are forced to conclude that the machine M sub diagonal does not exist. And that's a contradiction, which means that we have proved that the diagonal language is not decidable.